In this video, I'm going to talk about ordinary versus singular points in differential equations. Let's go ahead and start off with a second order homogeneous differential equation that has the following format. P of x, uppercase P of x, y double prime, plus Q of x, y prime, plus R of x, y is equal to 0. We are making the assumption here is that P, Q, and R has nothing in common other than 1 as factor. And also, P, Q, and R, they have power series expansions. So let's go ahead and define ordinary versus singular points in maybe 3 different ways. So first way is this. Very easy way. Let's consider a point x naught. A point x naught is ordinary if P of x naught is not equal to 0. We will call a point x naught an ordinary point for this differential equation if P of x naught is not equal to 0. Otherwise, it would be considered a singular point. Okay, so that's one way of defining it. Second way of defining it is this. We could take this equation, kind of rewrite it in such a way so that y double prime has a coefficient of 1. So in that case, we are going to have y double prime plus, let's say, lowercase p of x, y prime, plus q of x, y is equal to 0. As you can see, this p of x and q of x are nothing but, so let me write it down here, p of x, you can think of it as q of x over capital P or uppercase P of x, and little q of x is nothing but r of x divided by uppercase P of x. But this is just a side note, okay? So let's consider this differential equation, second order homogeneous differential equation in this format. In this case, we are going to define a point x naught to be an ordinary point if limit x approaches x naught, P of x, this P of x, exists and finite. So exists and finite in the complex plane. This limit exists means actually it probably would be finite, right? That's what it means for limit to exist. And similarly, limit x approaches x naught and q of x exists and finite. And this has to be an and. Both of these conditions have to be true for x naught to be an ordinary point. Otherwise, we will call it singular. So otherwise, x naught is singular. So remember here, both limits have to exist and finite in the complex plane, okay? So limit x approaches x naught, P of x exists and finite, and limit x approaches x naught, Q of x exists and finite. Then we are going to call this point x naught an ordinary point. Otherwise, we'll call it singular. And yet the third way of defining it is this. A point x naught is ordinary point if P of x and Q of x both are analytic at point x naught, are analytic at x naught, okay, or some small neighborhood containing x naught. If that is not the case, otherwise we'll call it singular. And let me kind of elaborate here. What do I mean by analytic? You may or may not have heard of this term. This basically means that a function is differentiable in the complex plane. That's what it means, okay? So analytic means is differentiable in the complex plane. So these are the three different ways you can define ordinary versus singular points. And now let me give you some examples. I'm going to give you maybe a few examples. So let's go ahead and give you the easiest example. So let's say example 1. It's not a differential equation. It's just a power series expansion of 1 over 1 plus x squared. Okay, we want to find the radius of convergence and the discontinuities. Okay, so this is the same as 1 over 1 minus x squared, right? Which is going to be 1 minus x squared plus x to the power 4 minus x to the power 6 plus dot, dot, dot. It keeps going. Now, if you look at this 1 over 1 plus x squared, you can see division by 0 happens when 1 plus x squared is equal to 0, right? So 1 plus x squared is equal to 0. That tells me that x must be equal to plus or minus I. I is the imaginary number. I is equal to square root of negative 1. As you know, I is equal to square root of negative 1. Now, if you look at the complex plane, by the way, this is an expansion around 0, right? X equal to 0. So if you look at the complex plane, so this is the real axis and this is the imaginary axis or x or y. So my 0 is right here, okay? This is power series expansion about 0, right? So 0 is right here. I is going to be here and negative I is going to be right here. So the distance between these 2 points. So the way you find the discontinuities is basically, the radius of convergence is basically you go from the point around which you expand to the discontinuity or where you are doing the division by 0. So it's just 1 unit up and 1 unit down. So your radius of convergence, let's call it R, is going to be 1. And the interval of convergence is going to be from negative 1 to 1. So that's example 1. Let's give you another example. Let's call it example 2. In this example, I will actually introduce a second order homogeneous differential equation. So let's consider it to be 1 minus x squared times y double prime plus 3x times y prime plus 3y is equal to 0. Now, if you look at this differential equation, you notice that the coefficient of y double prime is 1 minus x squared. So for what values of x would make this a 0, 1 minus x squared? Obviously, is going to be x is equal to plus or minus 1. So my radius of convergence is 1, given that I am expanding the power series at around x equal to 0. So radius of convergence 1, and it goes from negative 1 to 1, the interval. However, there is something else I want to introduce here that's very important. Let's divide both sides of this equation by 1 minus x squared. That's going to give me y double prime plus 3x over 1 minus x squared times y prime plus 3 over 1 minus x squared times y is equal to 0. Now we know that the singular points are 1 and negative 1. So let's go ahead and do the following. I'm going to multiply this guy by x minus 1. Okay, so let's take 3x over 1 minus x square, okay, multiply it by x minus 1, okay, and take the limit of it as x approaches 1. If we do that, we get the following: limit x approaches 1, okay, x minus 1 times 3x over 1 plus x times 1 minus x. So I can write it as x minus 1 and introduce a negative sign in front. And this is going to cancel out. That's going to give you limit x approaches 1 negative 3x over 1 plus x. Okay, so what happens if x goes to 1, the limit is nothing but negative 3 over 2. So this limit does exist, right? Now let me go ahead and take a limit of this guy by multiplying it by x minus 1 whole square. So limit x approaches 1, okay, times x minus 1 whole square times 3 over 1 minus x square. Then I can simplify it a little bit. So it's going to be 1 minus x whole square is the same as x minus 1 whole square times 3 divided by 1 minus x square is 1 plus x times 1 minus x. And here the limit, of course, x approaches 1. And let's continue with this. So limit x approaches 1, and this becomes 3 times 1 minus x over 1 plus x. As x approaches 1, what happens to this? It becomes actually 0, right? So this limit does exist as well. So note that I have multiplied the p of x, okay? I have multiplied the p of x, which is this guy, p of x is equal to 3x over 1 minus x square. I multiplied it by x minus 1, and I multiplied the q of x, which is this number here, or this function here, 3 over 1 minus x square, and multiplied it by x minus 1 whole square, x minus 1 whole square, and I took a limit of it as x approaches 1. And both of these limit exists. So if you have a singular point for a differential equation for which these two conditions are satisfied, it is called a regular singular point. Regular singular point. Remember, you multiply p of x by x minus 1, or rather x minus x naught, as x approaches x naught. In our case, x naught happens to be 1. So you multiply it by x minus x naught and take the limit as x approaches x naught. If that limit exists, and then you multiply q of x by x minus x naught whole square, and that limit also exists, then the point in consideration, x naught, is called a regular singular point. If one of them is not satisfied, that means between these two limits, if even one of them does not exist, then it is called irregular singular point. So we have defined regular singular point and irregular singular point. So let me just quickly write it here just to refresh your memory on this. So limit x approaches x naught, x minus x naught, little p of x exists, okay? Or limit x approaches x naught x minus x naught whole square little q of x exists. If this and this exists, then we call it a regular singular point. Otherwise, we call it irregular singular point. I hope that this discussion was helpful. Thank you very much.